Professor Dave and Chegg here. One of the most important analytical tools in acid-base chemistry is titration. This technique allows us to determine the concentration of an unknown acid or base by reacting it with an acid or base and taking some simple measurements. This topic can get overwhelming, but let's break down the math as simply as possible.
We must first understand that titration is a form of stoichiometry, where a neutralization reaction can be monitored with a colored indicator to determine the concentration of an acid or base. The indicator will turn the solution a certain color once a precise stoichiometric amount of acid or base has been added so as to precisely neutralize the other substance. But now that we have a better understanding of acid-base calculations, we can take a closer look at the pH as it changes during a titration. First, let's examine the simplest situation, the titration of a strong acid with a strong base, by looking at this titration curve. Let's say we have 25 milliliters of 0.1 molar hydrochloric acid, and we are titrating with 0.1 molar sodium hydroxide. At first, there is only hydrochloric acid in solution, so the pH starts off quite acidic, around 1. As base is added, some of the acid is neutralized, slowly raising the pH. Once 25 milliliters are added, this is enough to reach the equivalence point. This is where there is precisely enough base present to neutralize all the acid, which means there will be no acid or base, only water and the sodium chloride salt that results from the acid-base reaction, so the pH will be completely neutral at this point. Then, as more base is added, the pH begins to climb into basic territory, as there is no acid left to neutralize it. When titrating using any strong acid and strong base, the equivalence point will always be 7, but things get trickier when one of the species is weak. Let's examine a situation where we keep the previous volumes and concentrations the same, but this time a weak acid like acetic acid is titrated with strong base. Because acetic acid is weak, not all of it will ionize, which means there is less hydronium in solution than for a solution with hydrochloric acid of the same concentration. So we begin at a pH of 3 this time. We can see that as sodium hydroxide is added, the pH will climb more rapidly than the previous example. The equivalence point will also climb higher than the previous example because even when enough base has been added to neutralize all the acetic acid, there will then be acetate in solution, which is strong enough to react with water in solution to generate some hydroxide, meaning the solution will be basic at the equivalence point. After the equivalence point, the pH will continue to climb as more base is added. We can see that the behavior for each curve is different leading up to the equivalence point due to the initial discrepancy in acidity, but once the acid is completely neutralized, the behavior after the equivalence point is identical, as this simply represents the addition of more hydroxide. Now that we know how pH varies during titration, it's time to learn how to do quantitative calculations regarding the pH of a solution at various points during a titration. These will essentially be stoichiometric calculations, because we will simply have to know how much acid or base we started with, also called the analyte, and how much was neutralized upon the addition of a certain volume of titrant. This allows us to calculate the amount of hydronium or hydroxide remaining in solution, and therefore the pH. Let's return to our previous example of 25 milliliters of 0.1 molar hydrochloric acid being titrated with 0.1 molar sodium hydroxide. We can calculate the pH of the solution after any amount of base has been added, so let's do this in increments of 12.5 milliliters, from 0 to 37.5. This will be easy since both the acid and base are strong, so we can assume complete dissociation of both species. Before any base has been added, we simply have 0.1 molar hydrochloric acid, which will be equal to hydronium concentration, so we can just take the negative log to get 1 for the pH. After we start adding base, we need to figure out how many moles of acid are neutralized. 25 milliliters, or 0.025 liters, times 0.1 moles per liter will be equal to 0.0025 moles of acid. If 12.5 milliliters of base are added, that will be 0.00125 moles of base. That is enough to neutralize half the acid. So we will get 0.00125 moles of acid left over, divided by the new volume of 0.0375 liters. And that gives us a hydronium concentration of 0.033 and a pH of 1.48. After 25 milliliters, we have precisely the same amount of acid and base, so we will get a completely neutral solution of pH 7. After 37.5 milliliters of base, now we will have excess hydroxide. 25 milliliters, or 0.0025 moles, were neutralized by the acid, so we have an additional 0.00125 moles of hydroxide remaining. Dividing by the total volume of acid plus base, which is 0.0625 liters, gives us a hydroxide concentration of 0.02 molar for a pOH of 1.7, and subtracting from 14 gives us a pH of 12.3. Now let's try the same thing but use acetic acid instead of hydrochloric acid. Acetic acid has a Ka of 1.8 times 10 to the negative 5, so before any base has been added, we can use the following expression, recognize that the two products will be present in equal amounts, so we can just say hydronium concentration squared, and rearrange to solve for hydronium, which will be 1.3 times 10 to the negative 3, giving a pH of 2.87. Next, let's add 25 milliliters of 0.1 molar sodium hydroxide. This is precisely enough base to neutralize all the acid, which means all 0.0025 moles of acetic acid will be converted into 0.0025 moles of acetate ion, which divided by the new total volume gives us a solution that is 0.05 molar in acetate. Now, acetate will react according to this equilibrium, so let's bring this to the top, and we see that we will need the Kb for acetate, and this can easily be derived from the Ka of acetic acid. From here, we know the acetate ion concentration. We know the two products will be equivalent, so we can solve for hydroxide concentration, which will be 5.3 times 10 to the negative 6, giving a pOH of 5.28, and subtracting from 14 gives a pH of 8.72. This is why the equivalence point is greater than 7, because of the hydroxide generated by the acetate ion. We can do calculations with other amounts of base as well. Once again, the substance being analyzed is called the analyte, and we can calculate its concentration by adding another substance called a titrant. The titrant is either an acid or base that will react with the analyte, and when precisely enough titrant has been added so as to completely neutralize the analyte, the solution will glow a vibrant color due to an indicator that is present in solution. This is called the equivalence point. When this occurs, we measure the volume of titrant that has been added and perform our calculations. So once again, when performing titration, the actual data being collected is the volume of titrant added, so it will be important to check the reading on the burette at the beginning and end of the titration, so that we can subtract the final volume from the initial to get the volume of titrant that was added to the analyte. Say we are performing a particular titration whereby we want to find out the concentration of a solution of hydrochloric acid. We will use sodium hydroxide of a known concentration as the titrant. So here is the equation that describes this reaction. We will perform the titration, record the volume of base that was used to reach the equivalence point, and then we do a simple three-step calculation to get the concentration of the acid. First, we convert our volume of base into moles of base by using the concentration of the base. Then we use the stoichiometric ratio, or stoichiometric factor, to convert from moles of base added to moles of acid neutralized by that base. In this case, it's 1:1, because every hydroxide in solution will react with one proton to make one water molecule. And lastly, we convert the moles of acid neutralized into a concentration by dividing by the volume of the initial solution. So let's say we actually perform the titration using 50 milliliters of hydrochloric acid of unknown concentration. We titrate with 0.25 molar sodium hydroxide, and it takes 35.24 milliliters to reach the equivalence point. Now let's go through the three-step calculation we just outlined. In step 1, we convert the volume of base into moles of base, making sure to convert from milliliters to liters first, and then multiplying by the concentration to get moles. So it took 0.00881 moles of base to reach the equivalence point. Next, we simply understand that every mole of base will neutralize 1 mole of acid, due to the 1:1 stoichiometric ratio, so we just get the same number for the moles of acid that were neutralized by this many moles of base. Then lastly, we take the moles of acid that were in the acid solution and divide by the initial volume of that solution before we added any base, which as we recall was 50 milliliters, or 0.05 liters, and that gives us 0.176 molar as the concentration of the acid solution. Let's do one more for practice. Say that it takes 38 milliliters of 0.75 molar sodium hydroxide solution to completely neutralize 155 milliliters of a sulfuric acid solution, which is H2SO4. What was the concentration of the acid? So let's perform the calculation just as we know how to do, except let's point out one key difference. Sulfuric acid is a diprotic acid, meaning it can potentially donate both of these protons, which it will do in the presence of strong base like hydroxide. So let's keep that in mind when assessing stoichiometry. To begin, 38 milliliters can be converted into 0.038 liters, and then we multiply by the concentration to get 0.0285 moles of base. Now it takes 2 moles of base to neutralize each mole of acid, since each mole of sulfuric acid reacts with 2 moles of sodium hydroxide to produce 2 moles of water. This means we have to cut this many moles of base in half to get the moles of acid that it reacted with, which we achieve using this conversion factor to give 0.0143 moles of acid. Then we know that we began with 155 milliliters of sulfuric acid, which we can convert to liters. So let's divide our moles of acid by 0.155 liters, and we get 0.092 molar sulfuric acid.
With that, we now have a better understanding of titration as an analytical technique for determining the concentration of an acidic or basic solution. Professor Dave for Chegg. See you next time.